Hi folks, it's Dr. P. Today I want to talk to you about how to use breadboards. This is specific for my circuit analysis students. I have another video for my digital systems students about how to use breadboards. You folks are going to have very different needs for how your breadboards are going to be used, so it's worth making a separate video. The first thing I'd like to do is discuss the anatomy of a breadboard. Your breadboards are actually made out of a lot of separate components that are kind of all just kind of stuck together on one nice metal support. There are a bunch of different sections here. We've got binding posts, which can be used for connections to different power supplies. And then we have various sets of actual breadboards. So you'll notice that there are along the top, there's some that look like kind of horizontal. And then if you look at these, we have some segments where we have a big trench. And then we have some holes kind of to both sides of the trench. And then we have these vertical lines that go on the outsides of those. I have some connections that I made with wires because I use this breadboard all the time. And having these connections kind of like stuck in there makes it easier for me to use the breadboard. But your breadboard, when you first get it, is not going to have anything connected. So let's discuss exactly what all of these things are. I'm going to show you a different breadboard. And it has the same typical features where there's a big trench in the middle. There are some rows off to the sides, and then there's a column. If you were to look at the underside of this, there are actually little metal terminal strips. And those show you what connections actually exist inherent to this breadboard. What this shows me is that the trench is electrically isolated, and then on either side of the trench are connections along each row. So if I were to stick a wire in one of the pins in each row, they would be connected. Okay, so this is basically like a hidden feature underneath our breadboard that has an electrical connection for us such that we don't have to throw any other wires in here. And then along the sides, there is a long power rail. You'll notice that this specific breadboard actually has some gaps, which is why I have these wires in place to make sure that there's a connection from top to bottom. So the way a breadboard works is trench. Off immediately adjacent to the trench is rows, with each row on either side of the trench being electrically isolated, and then power rails, which are columns. The idea of the power rails is that I can have a connection to, let's say, high potential here and low potential here, and because those are so commonly used, I have connections on either side, all the way up and down my board. So if we look back here at this breadboard, you'll notice that there's some color coding that happens along the sides and along the top. The color coding is kind of a useful way for us to pick, let's say, low potential is blue and high potential is red. So it's just kind of a visual reminder of what's connected here. It's really important for us not to make any shorts between high and low potential because that would lead to some melting at the very least. So those visual reminders are nice. We can kind of have an easy picture of what's connected in those rails. And if you'll notice, these rails have these painted lines on them, and the painted lines are continuous, which means if I were to take this breadboard off and look at the back, I would see that that power strip goes all the way down. There's no gaps like there are in that other breadboard. And then on the top, there's just a convenient horizontal power header so that we can use connections to high and low potential here as well. And because the line, again, is continuous, that just means that we don't have to worry about any gaps. I want to point out that some of these breadboards have been a little loved, so there might be some gaps in the paint, and that's just because they're worn out. These specific breadboards, the Jameco Value Pro breadboards, they do not have any gaps like that other breadboard I showed you. So you can be assured that if you make a connection up here, you make a connection down here, those two things are going to be connected together. So all a breadboard is a convenient mechanism for us to make electrical connections without us having to solder or wire wrap or do any other type of annoying thing where we connect components together with alligator clips. It just allows us to have a nice stable platform for our devices without having to worry about any of the underlying connections. I want to point out these binding posts. Okay, so there's 4 binding posts on the top of your breadboards, and a binding post is just a small fitting that can, in the top, accept a banana plug. Okay, so what we can do is we use these binding posts to connect the breadboard to the power supply, and I'll show you how to do that in a bit. Inherently, there's no connection between this binding post and this breadboard, right? There's no electrical connection there. There's no wires hidden in this metal frame. So if you look at the binding post, it can actually be screwed and unscrewed. And if you unscrew it, there's actually a little hole that exists inside the metal cap of the binding post that connects into where the binding post would go. So what that means is if I want to connect my binding posts or my breadboards to the power supply, I would use a banana plug that I plug in. But just like this on its own has no connection from this post to my power rails. So what we need to do is unscrew the binding post, find a wire, look for that hole that exists in the binding post, stick the wire in, and then screw the cap back down until it makes a nice tight connection. Be careful that the connection that you make with the binding post is on the metal part of the jumper lead and not the plastic part. You should be able to tug on it and it shouldn't come out. Okay, but I've seen many students connect down and really kind of crank this down on the plastic part, which means that no electrical connection is made, right? We need conductor on conductor, not conductor on insulator. And then you take the other end of the jumper wire and just stick it into, here I would use obviously the red connection, okay? So this is going to be my connection to high potential. This is going to be my connection to low potential. So I'm going to take a black wire and I'm going to stick it in that binding post. Again, I'm going to be careful that I clamp down on the metal and not the plastic part. And once that's nice, I make a gentle tug, make sure that the wire doesn't come out, and I'm going to connect this on the top rail. Before I connect this into the power supply, I would like to kind of point out the different types of connectors that we have. So this is a banana plug. It's so-called because it's shaped like a banana, and if you notice, there's actually a little hole, and there's the banana part. So the nice thing about the hole is if I needed to connect 2 of these banana plugs together, it seems like they would not fit, but you can actually stick one into that hole, and now you've got a connection between 2. So that's a nice trick that we can use to make our banana plugs longer if we need to. And then another option that we have for connecting a banana plug, which we know can go right into a binding post, but if we need another option, we can use an alligator clip. So an alligator clip is named for obvious reasons, right? It looks like a snapping alligator. And we can stick that alligator clip right on the banana part, and then we can connect this to just about anything, right? We can actually connect that on the binding post. We can connect it either to the banana plug itself or the hole in the banana plug. We can connect it to a jumper wire end. We can connect it to the end of a component lead, right? There are so many options. We can even connect 2 alligator clips together. Okay, so there's a lot of options here as far as connections go. But usually what we want to do is find the connection that's the most secure, and usually just banana plug binding post is going to be good. If we want to use an alligator clip to connect to something on the board, which you might have to do several times in circuit analysis, I recommend that you connect it to a jumper lead, a jumper wire, like so, and then connect the other end of the jumper wire into the breadboard. Okay, sometimes people like to make connections directly onto a component lead. So I'm going to grab a resistor, and I'm going to show you how you could do that. So if you've got a resistor placed in your breadboard, what you can do is you can take your alligator clip and just stick it onto one of the legs. Now the problem is sometimes you've got so much force pulling on these that sometimes it actually can remove a leg of a component from the breadboard itself. So just be careful about that. In those situations, it's better to connect to a jumper wire and then connect that jumper wire into the breadboard instead. Okay, but you've got a lot of options as far as how can you connect things and make connections onto the breadboard. Let's talk now about making connections on the breadboard. So let's start actually making some useful circuits. So what I'm going to do is I'm going to connect my 2 binding posts to the banana plugs, and I'm going to plug those into the power supply. Now I'm going to be making another video about how to use all of the different equipment. I actually have a different function generator than the one you're going to be using. So at some point when I get a version of the function generator you use, I'm going to make a detailed video about how to use a power supply, the tabletop multimeter, the function generator, and the oscilloscope. So those are going to be your tools to help you analyze your circuits. So just that aside, I'm going to just connect to 5 volts. So I've got something going on here. And I know you can't read the readout, but it's reading nominally 5 volts. So now I have a connection between the banana plugs that come from the power supply to my binding post, and from my binding post to the breadboard. So what that means now is all of the red painted spots have a connection to high potential of 5 volts, and all of the blue painted lines are connected to ground. Okay, and that's just because I have all of these peripheral connections in. So I could use the top rows, and I can use the columns along the sides. And that's just kind of nifty, handy for me to use. Sometimes you might be using a DC source and a function generator, in which case you might not necessarily want to be limited to having all of these rows and columns being connected to just one thing. So the first thing I want to do is talk about how to make simple series and parallel connections with resistors. What I see a lot of is I see my students kind of like putting in a resistor and then taking a wire and moving it somewhere else and then having another resistor connected in and then measuring, let's say, between these two ends, okay, if they want to measure the resistance or something. This isn't wrong. Okay, so this would be a series connection of 2 resistors. Notice that we have one lead plugged into one spot. The other lead has to be plugged into a different spot, right? And that trench isolates one end to the other. Then I've got a wire that's in the same row as this lead going to another spot that's electrically isolated otherwise from over here. The same row, there's a lead to the resistor, and then the other lead of the resistor goes in a separate spot. Okay, so this isn't wrong, but it's kind of an overkill approach. So I always subscribe to the less is more approach of building circuits. So I want to use as few wires as possible. I want to be able to look at the breadboard and really have a clear understanding of what's going on. So usually when I connect resistors together, rather than using a horizontal approach, I like to use a vertical approach. So we know that, for example, these rows are numbered, right? So if I were to put one end of the resistor in row 10 and another in row 20, that those would be electrically isolated from each other, and that's what I want, right? So what I can do is I can take the resistor and I can kind of plug it in a vertical fashion. Then I know I need to connect this lead to another part of the other resistor. So let's say the other resistor now will be connected between rows 20 and 30. So what I've done here is I've made a series connection of 2 resistors that requires no wires. All I have to do is make sure that these resistors leads are in a common row here so that they're connected. Okay. One common mistake that I see students make is that they will do this. Let's say put one leg of the resistor in row 15 and the other leg of the resistor in row 15. This is a problem because remember, there's a metal wire underneath that we can't see that is connecting the 2 leads of this resistor together. So essentially, if I were an electron and I had the choice of traveling through this resistor or traveling through the wire underneath, I would choose the wire underneath, right? Because I'm going to choose the path of less resistance proportionally. And if the terminal strip underneath has no resistance, I'm going to go through that exclusively rather than going through this resistor. So it's important not to short out 2 ends of a resistor. This is a short. It's not a dangerous short. This isn't the kind of short that's going to start a fire. But what I mean by short here is this resistor is basically non-existent from a standpoint of electron flow, right? So we do not want to have things connected that way. So for a series connection, I just like to make these nice vertical connections. Okay, and then I'm not tempted to short the 2 leads together. And then I just make sure that one lead is connected with the other, and I make another vertical connection. Okay, so I have 2 resistors in series here. To have 2 resistors in parallel, we need to make sure that both nodes are shared. Here, only one node is shared. So the great thing about the arrangement on a breadboard is that when I want to plug 2 components in parallel, I just connect them so the top leads are in the same row and the bottom leads are in the same row. Okay, so breadboards are actually really great to do these connections. All right, I did not have to do anything fancy here. I mean, again, I dislike the horizontal arrangement of resistors because it just leads to kind of what I see as like a sloppy or a messy breadboard, which isn't a problem. But when it comes to debugging things, it's going to be a lot easier if you can look at your breadboard, and especially if I can look at your breadboard and immediately tell what's going on. So the fewer wires and things that are going all over the place, the easier it's going to be to debug. So I would recommend getting into nice, neat breadboarding habits early on, because our circuits are just going to get more and more complicated throughout the semester. So good habits start early. Start early with your, nice clean breadboarding of especially resistors. So try not to have wires all over the place. Sometimes it's unavoidable, but the fewer things you have, the better. Let's connect a simple circuit. So I'm going to show you the circuit diagram. There's a connection to the power supply. The power supply is in series with a resistor, and then that is in series with a combination of two parallel resistors, and then the idea would be to measure the voltage drop over the parallel combination of resistors. Remember that we already have connections to power and ground inside the breadboard. So what I want to do is I want to take one end of a resistor, R1, and connect it between high potential and another spot on the breadboard. Right now that could be anywhere. So I'm going to take my resistor and I'm going to connect it between a high power rail and anywhere else on the breadboard. Okay, so now I have the 5-volt spot here, okay, and then I've got my R1 connection. Then I need my two parallel resistors. So what I'm going to do is I'm going to do exactly that same trick that I did before, where I've got these two in that vertical fashion. Finally, I need a connection back to ground. So I'm going to find a black wire, which I'm running kind of low on these days, because I've been soldering a lot of parts. Here we go. Between this parallel combination and my blue low potential row here, okay? So notice that one of the benefits of this arrangement of resistors on the breadboard is that it looks like the circuit diagram, right? If I were to overlay the circuit diagram on this, you can really easily go between the circuit diagram and this breadboard. So it's really nice, easy to see what's going on. Okay, so that's how I would make that connection. Now, if I want to connect my multimeter to this, I would use alligator clips, right? And I could connect here and here. But again, perhaps I'd want to use alligator clips connected to jumper cables so that I don't have the issue of pulling any of these leads out of the breadboard, which can happen if there's just a lot of force being applied. Okay, so that's not too bad. That would be an easier type of circuit. And again, trying to make your breadboard arrangement look like the circuit diagram is going to help when it comes to debugging things. One thing that I'd like to point out that I want you to do, I want you to get in the habit of using red wires for high potential, especially with DC. With an alternating source, maybe you want to use a white wire or something. But with a DC source, definitely use red for high potential and black for ground connections. And don't use any other colors for high potential or ground. Why would I say that? When we have one color for high potential that's red and one color for low potential that's black, and they're reserved for only those two things, we minimize our chance of having an accidental short. I know that red and black can never touch each other, otherwise I'm going to have an issue. And it also helps me to indicate which parts of the circuit are high potential and low potential. It's easier to get that distinction in a digital systems class where we literally only have two different things, high or low. It's a little bit harder to understand in circuit analysis because we have a lot of intermediate potentials. Like here, this is neither high or low potential. So I could use literally any other color of jumper wire, orange, yellow, blue, green, whatever I wanted here. But I would not use red or black here because this is neither high potential nor ground. And again, the distinction between black only for ground and red only for high potential just helps us to not only keep our circuit more organized, but help prevent short circuits. I can also kind of immediately see, ooh, black wire, that's connected to ground. Now I know where to put the reference clip for my voltmeter or for my function generator or for my oscilloscope. So when we're doing more advanced measurements, then also knowing where ground is really quickly and easily can kind of help us for where we can make some connections. Let's do a slightly trickier circuit. So this one actually has two connections to power. There's a DC source and there's an AC source. If you look, it's actually very similar to the simple circuit that we did, with the exception that one of the resistors has an AC source kind of going through it before it goes to ground. Okay, so I'm going to use my function generator here. I'm not going to plug it in or anything, but you're going to have a very similar connection with your function generator that has alligator clips. So what we need to do is we need to physically take one of these resistors out, okay, and we can connect this maybe in an intermediate spot, and then I'm going to go out on a limb here and I'm going to connect that red clip to one end of this resistor. And then I know the other end of this needs to go to ground. And as long as I plug this in anywhere where there's a ground connection, which could be anywhere in this row or anywhere in the blue columns, then we're good to go. So if we look at this, again, it's very similar to how the circuit diagram looks. I have resistor R1, resistor R2 that goes through the function generator before returning to ground, and then resistor R3. These are equivalent resistors, right? These are all identical to each other. If you were actually building this in a class, you'd want to make sure that you took the correct resistor out, right? If this is like 100 and this is 200, right, you just want to make sure you use the correct one. But if they're in parallel, it doesn't make a difference if I have this one on the left or this one on the right, because parallel components can be interchanged with no problem. Okay, so again, the takeaway here is let's try to make our circuits as simple as possible. Less is more, so use fewer wires and more clever positioning of components. Try to make your breadboard look like your circuit diagram so it's easier to debug. And then reserve connections for high potential with red wires and low potential to black wires. I understand that starts to get a little tricky when we have two different sources, right? I have an AC source and a DC source. So this obviously has a red paint on the plastic. So just understand that, again, we don't want to have this connected to any of the black wires. So that's really just to help prevent against shorts. I'd like to discuss some of the specialty components that we're going to use. The first is a potentiometer. So a potentiometer has 3 leads to it. The 2 outer leads are connected to the fixed resistor, and the inner lead is the wiper. So if we were to rotate the dial on the top of the resistor, or the potentiometer, we could actually change the position of the wiper. Okay, so just understanding the 3 connections here, the 3 pins here are related to the 3 pins on a circuit diagram as shown. The rest of the components I'd like to discuss in this segment of the video are components that have polarity to it. That means that there is one correct way to plug them in. The first is a diode. So this is just a regular old diode. It's not a light emitting diode, although I guess it could be if you applied enough voltage to it, but it wouldn't emit light for very long before it blew itself up. As you notice on the case, there is actually a painted stripe, and that painted stripe corresponds to the part of the circuit diagram where there's the line at the edge of the arrow. So current only flows through a diode in the direction of the arrow. So here, current would be able to flow in this direction. Okay. The next component is a light emitting diode, or an LED. And these are just useful in general if we want to have some type of an indicator. There are 2 ways to determine the orientation of an LED compared to its circuit symbol. High potential is connected to the long leg, and low potential is connected to the short leg. But another interesting thing to note, especially if the legs have kind of been mangled and it's hard to tell which end is which, the short end also is connected to a piece of the epoxy cap that actually has a little flat. You might notice that on this side it's actually round, and this side it's flat. Okay, so either use the flat end for low potential or the shorter leg for low potential. The other polar component that we're going to be using in this class is aluminum electrolytic capacitors. Okay, so these are aluminum electrolytic. They have 2 legs, and again, you can either go by the longer leg is high potential and the shorter leg is low potential, or if you notice around the casing, there's actually one side that has a painted stripe, and that painted stripe corresponds to the short leg. So short leg, painted stripe, low potential. And if you don't remember that, Notice how the stripe actually kind of has minus signs painted onto it, and that's kind of a helpful indication that that's going to be our low potential end. Okay, so again, these polar components, we need to plug them in correctly because there's only one correct way that they can be connected in a circuit. The last thing that I want to discuss in this breadboard video is about the type of component we're going to be using for op amps. So op amps are packaged in an integrated circuit. What that means is I can take one component and it contains all of the transistors, resistors, electrical connections, whatever that I need in one package. So these are packaged in DIP packages. Okay, so that means dual inline package. So these are called DIP chips. I have one here that is similar to the LM741, and actually it is an LM741. And this, I don't actually have the LM339 here at home, so this is actually a 324, but it's got the same arrangement of pins. And if you look, you can see that there are 2 columns of pins. Okay, so those are what we're going to use to make electrical connections everywhere. And we need to be careful with these pins because they can be easily bent. So what we don't want to do is just kind of keep them sitting around our tables and then we accidentally smush them with something. All right, you should have a piece of conducting foam in your kit. When you're not using your dip switches or dip chips, you should keep them in the conducting foam so they don't accidentally get smushed or bent. All right, so one thing that we can use to distinguish the size of these is by the number of pins. So this has 8 pins. It's called a DIP 8 chip. This is a DIP 14 because it has 14 pins. So let's understand a little bit about how these work. The DIP chips are going to have either a dot or a notch to tell us which end is up. The arrangement of the pins is important. I can't just use any one pin for anything. Each one has a specific purpose. So how do we know which end is up? This actually has a dot on it, which might be hard to see, but that tells me that that end is up. This one has a notch. That notch tells me this end is up. So I want to make sure that the notch or the dot is up. Sometimes a chip might have both a dot and a notch. Okay, well then that's just double the way to know which way is up. Printed on the package is going to be information about the manufacturer, the part number, possibly where it was manufactured. So look for the thing that says LM and then look at the numbers afterwards. That tells you the part. Something like N at the end just tells you that it's got a packaging, and I believe that means it's plastic packaging. That part's not too important. Okay. Some of them can be really worn out and it can be hard to read, but again, we can look at the label on the top of the chip to figure out what we have. We want to make sure we're using the correct chip. Fortunately for you, there's only 2 types of dip chips we're going to be using in this class, the 741 and the 339, and physically they look different from each other, so it's hard to confuse them. What we're going to do with these dip chips is we're going to exploit that trench. Okay, the trench, remember, makes electrical isolation between one side of the board and the other. So what I do is I take my dip chip and I place it so that it straddles that trench. Now I know which end is up, and I know that my pins here and here can be connected to other parts of my circuit without being shorted together. What you would not want to do is something like this, where you just kind of stuck this randomly at some point in the board. Then I'm going to have shorts between pins 1 and 8, 2 and 7, 3 and 6, and 4 and 5. That would be a problem. Okay, so throw it in across the trench. Now we have to understand the pinout of this chip. So what we're going to do is you're going to look at the pinout diagrams in the back of your lab manual, or you could find them on a data sheet. And we see that the numbering starts on the upper left and goes around in a counterclockwise fashion. So this would be pin 1, 2, 3, 4, 5, 6, 7, 8. And that helps us to understand what connections are made. So for example, the positive supply to this op amp goes to pin 7. Okay, so I'd make a connection here to the positive part of my power supply. And the low potential for the supply would go to pin 4, and so on and so forth. Okay, so that pinout is going to be our tool to figuring out how to wire this correctly. Anything that has NC or an X next to it means that there's no electrical connection there. or we're not going to be making use of that connection in this class, so I've omitted it from your pinout diagram. When you remove a dip chip from your breadboard, be careful not to do it in such a way that it bends the pins. Try to pull it out as vertically as possible. So what you might even want to do is take like a screwdriver or something and kind of pry it out from under the trench. Okay, and that's going to be the best way to remove it without damaging the pins. Right, you've got stewardship of your dip chips this semester, right? Because you've got your own kit of stuff. So take care of it. Don't let it, get bent or smushed or anything like that. I know mistakes happen, but try to get into good habits. Okay, let's take the dip 14 and stick it into the breadboard. Again, we're going to straddle that trench. And there's really no difference between this and the dip 8 except that it has more pins, right? So now we go from 1 all the way around to 14. And again, we can look at the pinout diagram to figure out exactly what connections need to be made. When we remove it, again, we want to be careful not to bend the pins. So we're going to do the best that we can to just kind of gently pry it off. All right, folks, that's all there is to say about breadboards. Until next time, stay well.